Okay, we'll be getting into a new lesson for Math 9, rotations and rotational symmetry. Symmetry, rotations and rotational symmetry. This is on page 361. So let's begin just by talking briefly about these windmills here. Rotational symmetry. You look at how a windmill rotates. And rotational symmetry is how often does something turn and then coincide into itself. Right? Like if you look at the blade on the top, where is it going to be like the blade at the bottom? When it's here. Or is it going to be like this blade when it's over? So this blade has 3 blades. So if you think of this as a 360-degree circle, 360 divided by 3 is 120. So this windmill would have rotational symmetry, we could say, every 120 degrees. Here, we have way more parts to this windmill. We have way more parts to this windmill here. Therefore, it would have rotational symmetry more often. Same thing with this one here. So you look at how they're the same and how they're different. Well, there's a lot of different ways. But the point is we're looking at them to show rotational symmetry. Like how often is something the same as it was when it started out as it turns. With some things that only happens once. With some things it happens multiple times. And with some things it never happens. So we're going to look at several shapes. I sketched several, so here's some examples, but I sketched several shapes that we're going to take a look at. Now you can either just follow along or you can make your own shapes. So I'm going to show you what I did. Then you can either pause this lesson or you can just watch. So I sketched several different shapes and I made a cutout of each shape. So we have this one. This one I lost. Oh, I just found it. You can see each shape has its own cutout. And I'm going to use these cutouts to illustrate rotational symmetry. Let's begin with this shape. Now the best way to do it is to have a dot to mark your starting point so that you know how you're turning. So I've made a 1/4 turn now, it does not coincide. I'm at the halfway point now, it coincides. I'm at the 3/4 turn, it doesn't, I'm back at the beginning. It only coincided once, which was at the halfway point. Okay? Let's look at this one. Here's the beginning, a 1/4 turn, a half turn, 3/4, full. It only never coincided. It had to come all the way back to its original place. So this is an example of a shape that does not have rotational symmetry. This has rotational symmetry only once. Let's look at the good old square. A 1/4 turn, it coincides. A half turn, it coincides. Oops. Sorry, I was moving too fast. I'm going to start again. There's a 1/4 turn. It coincides when it's in this corner. Move it down here. That's a half. It coincides again. Move it to this corner. It coincides again. Move it to your final corner, to its final resting place, coincides again. So a square coincides with itself 3 times. And you always count the original as well. So even if something has no rotational symmetry, you say that it has a rotational symmetry of 1. Okay. This guy has 2. This guy has 4, and you can probably guess that this triangle is going to have 3. It fits here, it fits here, and back to the original. Of course, I should label this to prove it. Make a dot on the tip. Goes down to this point, over to this point, back to the original. So again, you can do this activity yourself, make the shapes, and spin them around if you like. That part is up to you. It's an easy activity to do, sort of fun to do, whatever. Or you can just base it on your observations of what I did. It's up to you. But that's the basis of rotational symmetry, is how often can something turn, how often does it coincide with itself. That's the basic concept of rotational symmetry. Let's have a look at just want to very quickly grab a bit of sticky note and glue these shapes. To their sheets. Maybe I'll want it sometime in the future. It could have deep meaning. So I'm going to save all my cutouts that I worked so hard to make. Okay, let's go to page 362. And we have a nice example here of a cross. Now we look at what they did with this cross. You may already predict that this cross is going to coincide with itself 4 times. It starts here, it goes here. If you were to make, you can make a cutout of this if you like, but I'm not going to bother. If I made a cutout, I would turn it here, it would coincide. I would turn it to the halfway, it would coincide. I would turn it to the 3/4, would coincide. And I would turn it back to its original, and it would coincide. It would coincide with itself 4 times. And of course, each of these turns is a square, so it's 90 degrees each time. So it's just like the square that we looked at. The square turned 90 degrees each time. The triangle, which is 180 as opposed to 360, would be 60 degrees each time. A shape, let's read here. The shape coincided with itself 4 times in one complete term. That is during a rotation of 360 degrees. A shape has a rotational symmetry. Why do I keep saying symmetry? When it coincides with itself after a rotation of less than 360 about its center. So it has to coincide with itself at least once. The number of times the shape coincides with itself during a rotation of 360 is the order of rotation. The shape above has a rotational symmetry of 4. A shape that has to go all the way back to its starting point before it coincides has a rotational symmetry of 1. For each match, the shape rotated 90 degrees. We say the angle of rotational symmetry is 90 degrees, and that in rotational symmetry, the angle is very easy to find. Take the number of times it coincided, or the order of rotation, and divide that by 360 degrees. 360 in the brown box here, 360 degrees divide by the order of rotation. And with that, we're going to look back at the shapes that we did on the previous page to illustrate this concept. As I said, this was going to have deep meaning sometime in the future. This guy had 2 turns of rotational symmetry. 360 divide by 2. He has a rotational symmetry of 180 degrees. This guy had only coincided with itself when it came all the way around. So 360 divided by 1. In other words, it had to come all the way around before he coincided. We call that a rotation of 360. This guy had to turn to the halfway point, which was 180. The square coincided 4 times, just like that previous cross shape. The square coincided every 90 degrees. In other words, at every right angle. The triangle is going to be different. It only has 180 degrees. And it coincided with itself 3 times. So the triangle coincided with itself every 60 degrees. I hope everything is clear so far. So 360 divided by the order of rotation. Before we continue, let's write that down. 360 degrees divided by order of rotation. And this is true unless you're doing a triangle. That's 180, but we don't have any triangles in this lesson. I just threw that in there as an extra. But you really just have to be aware of the degrees, number of degrees your shape has. I mean, if you're doing a pentagon, that could be different. Okay. Anyways, let's have a look here. Beginning on page 362, we're going to look at which of these shapes have rotational symmetry. Determine which hexagons below have rotational symmetry. State the order of rotation and the angle of rotational symmetry. So I'm not going to do any sketches of these shapes. We're just going to look at them. So these are all 6-sided hexagons. So take a good look at this shape. As it turns, it's probably going to, you can see this side here, and when it turns, it'll coincide here, and it should coincide here as well. So it should have a rotational symmetry of 3, which would make it 360 divided by 3, 120. This guy, if you begin here, you pretty well are going to have to rotate it all the way to the bottom before it coincides. So it's only going to coincide at the halfway point. So 360 divided by 2 would be 180. This guy needs to be rotated all the way around, just like our original shape did before it would coincide. It's not going to coincide anywhere except if you bring it all the way around. So we say it does not have rotational symmetry. Or you could say it's 360 degrees before it's the same thing. Saying that it's 360 degree rotation or it does not have rotational symmetry, you're saying the same thing. It has to come all the way around before it coincides. And if you look at their answer key here, you can see that this guy has a 3, which is 120. This guy goes only twice, which is 180. This guy does not have rotational symmetry. We have some 364. We're going to do this activity on grid paper. So it says on page 364, rotate pentagon ABCDE 90 degrees clockwise about vertex E. Draw the rotation image. Rotate trapezoid FGH J 120 degrees clockwise around the rotation image. And then draw the rotation image. So let's do it. This will be very clear once I'm done doing it. So let me sketch the shape first. Size of the shape Doesn't really matter. I'll go 4 along the side, 3 along the bottom, and I'll go 2 spaces up for the top. So you want to rotate this shape 90 degrees about vertex E. Well, we better label these vertexes first. B is supposed to be over here, looking at the diagram. A, B, C, D, E. Vertex E is right here. So there's our rotation, and we want to rotate this shape 90 degrees. So we don't want to go half, we don't want to go over here, we only want to rotate it 90 degrees. We want to make one turn with this shape. So let's take point E and rotate point E 90 degrees. Now if I was to rotate it 180, I would go all the way over here, right? That would be a straight line. So if I'm doing 90, I'm going to go halfway. So this is now where your new point E is. Shape is rotating in this direction. So now you can simply draw all the other points around. So here we have point E, and we can make a straight line right here across to point D and C. How long did I make that side? 4. So 1, 2, 3, 4. And then I can go up by 3 and across 4. Not the best drawing I've ever done. I think we're going to do this example again. This is too messy. Okay, let's get over here and let's make the shape again. 4. And I'm not going to make the letters again. Here we have point E. We want to rotate this shape around point E. So that means it's going to flip up. It's rotating around point E and it's rotating this way. That means this entire thing is going to flip up here. So the shape is going to be here. If it was 180 degrees around point E, it would be coming all the way up, and we would have a shape like this that's coming like the point would be here, the triangle and the rectangle. So 180 would be flipping all the way up, right? But we're only doing a 90. That means it's going to be coming over here. Okay? So let's make a straight line of 4 squares, because we made the sides 4 squares before. We made the bottom a 3 and 4 squares across. And now we just have to we made the roof a 2, didn't we? Let's put it over here and go into the middle. And that's a 90-degree rotation around point E. If I'd done 180, then it would be this same shape here would be up here. So this flat bottom would be on the top here. I shouldn't have started at this point when I did the 180. I should have started here because the instructions are to rotate around point E. So then 180 degrees, just to show the flat part, this part, would be up here if we turned it 180. Let's do the other shape. This time we're doing 120 degrees and we're doing a trapezoid. Let's go to a clean part of the sheet. Let's make the top of the trapezoid a 5. Accurate enough, eh? it says rotate around point a vertex F. If you look at the original diagram, that's this point here. And we don't really need to label all the other ones. We just need to label this one. So it's saying 120 degrees. This time I'm going to have to use a protractor, because 120 is not an easy degree to get a measure of. 90 is a nice square, that's easy. Now I'm just going to have to grab a protractor. Hope you enjoyed your break. Somehow a protractor is always the most difficult instrument to find. There's just something about protractors. So put it here. This would be a 90, but we want 120, so we're going to go here. Make your mark so that you know where 120 degrees is, right? Because if it were straight, it would just be a 90, like pseudo before, the way we did it before. Could have just marked your 90 straight up, flipped everything. So here is, this is where 120 degrees is from point F. So this is as far as we're going to turn. So we're going to take this now, and we're going to make a line coinciding with point F, but not all the way up to the line, just the same length. So this is going to be the longest side of the shape right here as we flip it. And the longest side of the shape, originally I made it 5 squares. So I think what I'm going to do is actually measure it. 3 centimeters. Just so that I'm being as symmetrical as possible. We'll make that side 3 centimeters as well. This. And then it's just a matter of drawing the rest of the shape. So we've got your trapezoid. Let's look at how long did I make these guys. Roughly 2 centimeters. Oh, I've got a better idea. Make a mark at 1.5. And the length going up, that's about 1.5, okay. So then we'll go up, we found the middle, now we're going up to 1.5, and now all you have to do, so this is the top of the shape, and all you have to do is measure the very top of the shape. Here is about 1 centimeter, so that's exactly what I'm going to do here. Just make it 1 centimeter. There. Let's do another example that's not in the book. Let's just take a square and rotate it. Let's take a square. a 5 by 5 square and rotate it 180 degrees around this point here. This would be 90. If we're doing it straight up at 180, would be right over here. Alright? So take this, we're rotating this whole square 180 degrees so that it's going to sit over here. So the first thing we do is mark off 5 squares. And just, there's our original. That's what it moved to. Like it would have flipped up to here and then down here. So let's just make our brand new square after a 180 degree rotation. I made it too big. Should have gone up 5, I went up 6. Just ignore that. Okay, I think I didn't draw a perfect. Okay. Since I decided to do another example, I may as well do it correctly. So there's a 5, there's a 5, there's a 5. 180 degrees with my protractor, straight line, make another 5, and another 5, and another 5. This should have been a very simple example, but I overcomplicated it the first time. There we have it, a square after a 180 degree turn around this point here. So 270 would be down here and 360 would be back to where it started. Boom, done. Good. They've got another example here, but I don't think we need. We'll leave that one. I think we've done enough rotation examples. Let's get to our exercises. Page. Let's write them down first. Page 365. We'll do numbers 4, 5, and 6. And page 366. We'll do 8 and 9. And let's take a look at all those exercises. Here we have 4, 5, 6 on page 365. The angle of rotation symmetry for a shape with each order of rotational symmetry. So again, 360 divide by this number. Very simple. These are all four. We're assuming none of these are triangles. Okay. What is the order of rotational symmetry for each angle of rotational symmetry? So 60. Well, how many 60s are there in 360? 20. How many 20s? How can you figure that out? Simple division, right? 360 divide by 60 for this one. So this would, the order of rotational symmetry would be 6. So this is the question 5 is the opposite of question 4. What is the order of rotational symmetry and the angle of rotation symmetry for each regular polygon? Here we get a triangle, 180 divided by 3. A regular pentagon, you have the flat here. So obviously, as you're turning, you're not going to have symmetry. If you look at that, you're not going to have symmetry until it comes all the way back to its regular position. So here you would say what? Does not have rotational symmetry, or 360 degrees. A square we already did. I shouldn't need to rehash that one again. And then there's the regular octagon. How many times is that going to coincide? Well, if you're not sure, make a tracing for yourself and check it out. But you should be able to tell by looking at it how many times an octagon will coincide with itself. And then you're going to do once you know how many times it coincides, you're going to do 360 divided by that number. And for the triangle, of course, it's 180 divided by that number. All right, page 366, 8 and 9. Does each shape have rotational symmetry about the red dot? If it does, state the order and the angle of rotation. Again, the number of times that you, first of all, does it have rotational symmetry? If it does, how often? And then the number of times it coincides, divide that by 360. Okay, that's 8. 9 is the last example that we did. Copy the image on grid paper. Draw the rotation image after each rotation. So for this one, you copy the shape, and 90 degrees around point E, 180 around point M. And this one, so this is 1/4, this is the halfway point, and 270 is 3/4. 270. And here they're saying clockwise, so you're going to go this way. 180, if they're not saying anything, it's clockwise. Counterclockwise around this point, but you're not going to go this way, you're going to go counter or backwards. All right, that's it for this lesson. So again, on page 365, 4, 5, and 6, and on page 366, 8 and 9, there should be plenty more grid paper on the back table, should you find yourself needing any more. All right, let's click this off. 33-minute recording, not too bad.